20. Okay, so taking a look at number one, we should always try going through substitution, that there's no u value that will cause this to work. And also we don't have a rule for natural log for integrals. So this is actually integration by parts. And then the two categories here are algebraic and natural log. So natural log is natural log of x, and then there's a 1 that we can put there, and we treat that as algebraic. We can't do tab method since there's logs involved. So f has to be assigned natural log, and g prime has to be assigned the 1. F to f prime, and g prime to g. Okay, next up, we just follow our formula here. Fg minus integral of fg prime. There's always going to be one portion that's complete and the other portion that's incomplete. This integral of 1 over x times x needs to be continued to be resolved. We can get that to be integral of 1, which is power rule. And once we have that resolved, plug in your upper and lower bound, and then you can leave your answer in whatever form after the upper and lower bound is plugged in. Okay, number 2. U substitution is not going to work for this problem, so we're again relying on integration by parts, but now we can do tab method since there's no logs involved. X squared is our f, e to the negative 3x is our g prime. And then on the left column, we're going to keep finding the derivative until we reach 0. On the right side, for e to the negative 3x, we keep finding the antiderivative the same number of times as the derivative. But just be careful. E to the u is e to the u, but that negative 3x through u substitution will keep producing a negative 1/3 each time you go through u substitution. Okay, we pair our diagonals. Make sure we have alternating signs that's getting multiplied by either 1 or negative 1 for each of our terms. And then we're just inserting our upper and lower bound and cleaning up. Well, you don't have to clean up all the way. Any variation is fine here. Just be aware that sometimes we got to be careful around zeros. Sometimes we assume zeros will wipe everything out. Here, e to the 0 is not going to be 0. E to the 0 is going to be 1. So we do have a coefficient left over. We have a constant left over in our answer.
How did you determine it would be tab?
There's u substitution didn't work, And well, first off, we know it's integration by parts or tab method. And there's no logs involved. If there's no logs involved and your x squared can take the priority over exponential, then that's a good fit for tab. Yeah.
And you could tell it's going to be IBP or tab because there's the two terms.
That's right. You have two different types of functions that are being multiplied.
Okay.
And use substitution doesn't work.
Thank you. They have to be two different types.
They do. Yeah.
Okay. Yeah. They're really good. Otherwise, we should be exploring something else. Thank you.
So the acronym that I use to kind of help me, basically, you only have to worry about four types here. You have logs, algebraic, trig, and exponential. So whichever comes first, whichever is earlier in the acronym is going to take the priority for your F.
Thank you.
Okay, number 3. Looks like number 3 is a good fit for partial fraction since, well, use substitution doesn't work. And the denominator can be factored and the denominator has a higher degree than the numerator. So this is the cover-up method. Okay, first thing is we would like to have, we'll have a much easier time with evaluating this antiderivative if we can split this into two separate fractions. Let both denominators be linear. So we go through our cover-up method. So we solve for set both denominators equal to 0, solve for x, and then you're going to plug in to the original expression with that factored covered up. So if I want to plug in 2/3 into the expression, I'm going to cover up with 3x minus 2, 2/3 in for x, and that's going to clean up to be 2/7. Morning. And then if I want to test x equals -1/2, I'm going to cover up the 2x plus 1. And I'll get 1/7 if I solve for b. Okay, so really all we need is use substitution and natural log to get us through our antiderivative. Careful though, 3x minus 2 and 2x plus 1. They're both going to produce their own coefficient after use substitution. So 1/3 will come out of this one, 1/2 will come out of that one. And then we just make sure we keep track of our coefficients and our leftover constants. Okay, any questions 1 through 3? All right. 4. All right, number 4, definite integral from -1 to 1 of dx over cube root of x. So cube root of 1 over, if we ignore that dx there, we really want to consider, okay, what is it about this function here? 1 over cube root of x. So 1 over cube root of x does have a vertical asymptote at x equals 0. And the issue here is we're trying to find the area under this graph, but there is a break in the graph which is causing there to be some open space. So if you were to sketch this graph out and look at the region between -1 and 1, 1 over cube root of x looks something like this. If we're trying to find the area between -1 and 1, you're trying to find the area of this region. But anytime you have an open space, either caused by infinity or caused by the asymptote, you know you have to involve improper integral because this is not a closed region, right, from -1 to 1. So we're going to apply limit. So I'm going to do this left branch first. So this left branch is from -1 to 0, approaching from the left side of 0. Should have used variable here. Let me say, you can use any letter. Typically, it's A or B that we see most of, but it's really up to you. And I just want to get this ready for power rule. And then separately, we got to worry about this branch because this branch is also an open gap that we have to account for. And this branch is going from that asymptote to 1, but we're approaching the asymptote from the right side of 0 since this is where the graph is existing. Okay, so power rule here. So here, remember, anytime you see a one-sided limit and you're trying to evaluate, go for the integer value first, right? See if that is going to be okay. If that's okay, then there's nothing more that needs to be done. But if we get it undefined, then you can look at decimal values to see if you can make further conclusions. But here, 0 in for b is fine, right? 0 to 2/3 is a real number. And this becomes just -3/2. So this piece is converging. Let's see if we get anything out of this one. So that's a real number, 3/2. This one, 0 in for b, 0 to 2/3 is fine. That is still a real number. So we have -3/2 plus 3/2. We add our result together, we do get a converging value. Our integral converges to 0. Okay, any questions, first page?
What does it mean by, like, what does converges mean?
Convergence means that even though there's an asymptote, this area or this depth integral is approaching a real number.
Thank you.
As this is approaching -3/2, that's approaching 3/2, and so they're going to cancel out to give us a zero. All right, number 5, logistic differential equation. We're trying to find limit as t approaches infinity of p of t. And so really, we're just trying to get into one of these forms, right? If we get one of these forms, then we can look inside the parentheses or bracket, either pick out the L in the denominator within the fraction, or no fraction is going to be that first term. There's more than one way to do this. I just decided that I wanted to factor out 1/5,000, clear out all the denominators, and then I can get my expression inside to look like parentheses L minus Y, and I can just pick out the L value. Okay, any questions with 5? Okay, number 6. All right, suppose population of wolves grows according to the logistic differential equation, where p is number of wolves at time t. Which of the following statements are true? The limit is approaching 300. The growth is greatest when p equals 150. When p is greater than 300, the population of wolves is increasing. So let's first get this into something that is more easily identifiable in terms of looking for that carrying capacity. So I'm going to factor out. Let me rewrite this. So 0.01 p squared is the same thing as p squared over 100. I factor out a 1 over 100 p. I'm left with 300 minus p. So now it's easy to spot what our carrying capacity is. Our carrying capacity is 300. That makes sense. Answer choice 1 works. Growth rate is greatest when p equals 150. We know that our point of inflection is going to occur at L over 2. And since 300 is L, 300 over 2 is 150, our greatest growth rate is going to occur when p equals 150. So third one here, if the population is greater than 300, the population of wolves is therefore increasing. So what happens here is we're still left with this carrying capacity of 300, but it's possible that the population starts off more than 300, and let's say a natural disaster is causing that carrying capacity to decrease to 300, then it's not going to keep growing. So our logistic differential equation can look like this, right? Where it's hitting a ceiling because it's growing, or it could be like this, where it starts off greater than what the environment can support, and so it'll still flatten out towards that value. So if we're starting with a population that the environment is not able to handle, it'll eventually make its way down to that carrying capacity. So therefore, decreasing. So only answer choice 1 and 2 will work. Okay, does that make sense? Any questions with 6? Okay, number 7 should be pretty straightforward. Find your delta x, b minus a over n, create your chart. Okay, what do you notice about delta x when you found delta x? What'd you get for delta x? Yeah, so we got to hold on to that negative value in our formula as well. When we do our y equals y0 plus y prime delta x. Are you okay with 7? Number 8. Okay, so we know this is going to be working towards L'Hopital's, but we have to get there first. So let's assign this to be our y value. So that 3x is hard to work with in that exponent location, so we want to try to bring it down, but in order to bring it down without changing the overall value, let's do log differentiation. Let's involve natural log both sides. Okay, so now that 3x is free to move. Okay, so we know our goal. Our goal is to try to get this to either show us 0 over 0 or infinity over infinity so that we can apply L'Hopital's rule, but this 3x is not, or at least this x is not in the place where we can allow that to happen. So that 3 is okay, but we can just force that x to go in the denominator and make it 1 over x, right? Divided by 1 over x, same thing as multiplied by x. We're just rearranging that expression so we can get that condition that we want out of L'Hopital's. Are we good from here to here? These are the same same expression. It's just in the form that we prefer.
If we take the 3 down too, would that cause?
That's fine. If you can make it 1 over 3x, but I'm just gonna leave that 3 there. Just because eventually it's gonna have to come up back up anyways, so I'm just gonna leave it alone.
Yeah.
But yeah, you can move it down and move it back up if you want to. You'll get the same answer either way. So infinity here. So if I plug in a large number, 1 over infinity is 0. Natural log of 1 is 0. 1 over infinity, that's a really, really small number. That's also approaching 0. So we do have the condition that we are looking for. So now we can find the derivative of the numerator and the denominator separately. And then hopefully, after we reevaluate the new expressions, we should hopefully get a real number, and then we can resolve and solve for y at the end. So I'm going to get my expression ready for my derivative process, so I don't have to go through quotient rule here. Okay, natural log of u becomes u prime over u. Power rule for x to the -1 is just -1 x to the -2. Now, these actually cancel out, but if you want to rewrite it to make it more clear, you can do this. You can say, well, dividing by this is the same thing as multiplying by this, the reciprocal of this. So I can make it -1 x to the -2 over. So rather than dividing by this, I'm going to say multiply by 1 over -1 x to the -2. So if you write it this way, maybe it's easier for you to see, oh, these can actually cancel out. They could also cancel out in this spot if you're seeing it, but if not, feel free to move it to the same numerator denominator level, and that way that cleans up nicely. So let's evaluate the resulting expression's limit. If I plug infinity in for x, oh wait, sorry, I left out that 3. So u prime over u, but that coefficient of 3 needs to stay. All right. So infinity in for x, 1 over infinity is basically 0. So I'm basically left with 1 plus 0, which is 1. 3 over 1 is 3. So we have the limit on the right side, but we still have to resolve our goal. Our goal is to figure out what y is, because y is defined as the limit of this expression. So we're still stuck into that natural log. So raise both sides, e is the base. Y equals e cubed, and that's our limit. Okay, any questions? So I'm going to save worksheet 2 for tomorrow, but you guys can obviously work on it on your own. Any questions from worksheet 3 that you guys have? No, okay. And you should feel pretty good. Tomorrow.
What are all the trig rules? You should know.
You mean like integral or derivative?
Probably.
Yeah, I think just sine and cosine. It's good.
Thank you.
The only thing I didn't put on this worksheet is the arc length formula, but I have that showing up later in worksheet 2.
What's the trig identity I showed up the other day?
Oh, right. Sine squared plus cosine squared equals 1. That's right. Yeah. So we should know that one.